Hello everyone. After a long time I'm back. And if you remember last time we ended up the discussion with the real number line, and the real number line includes rational as well as irrational numbers, but the introduction of irrational numbers was a bit qualitative. Irrational numbers. Of course, this topic is very challenging, so we cannot have a detailed discussion, but at least I would like to have a more logical reasoning for why the square root of 2 is irrational. In other words, it cannot be written as a ratio of 2 integers. So, how will you prove this logically? Another example is pi. So, why is pi irrational? So, let's first start with the square root of 2. And let's say, now this proof is different from what you most probably have seen in the books. This is a bit lengthy, but it's very illuminating. So let's say it is possible. It's possible for me to write this square root of 2 is a ratio of 2 integers. So if this is true, and remember, we are talking about non-zero integers. I'll explain why that's important. So if it is true, then by definition, this is a number which, if squared, will give me 2. So if I take the square of it, and if I take the square of that, I'll get a squared over b squared. So these two say the same thing. And if this is true, then a squared must be equal to twice of b squared. So a squared must equal twice of b squared. Now from this we can draw two conclusions. One is that a squared must be larger than b squared. So a squared, because otherwise, if something is twice something else, that must be larger. The other conclusion is that because it is twice of something, whenever you have twice of something, that number must be even. So a squared must be even. Now, if the square of something is even, that thing itself must also be even. A must also be even. You can check it out. If it were odd, its square would also have been odd. Now, if a is even, similar to that, a can also be written, it must be twice of something. So let's say it's twice of something. Let's call that something c. Now let's plug this a equals 2c in that equation. What do we get? I combine these two, combine this equation with this conclusion, and I get this 2b squared as before, and a squared, so 2c squared. So 2 squared is 4, and c squared is c squared. Now because 4 is twice of 2, I can get rid of this 2, and basically this means that b squared is equal to 2c squared. That 2 here and that 2 here, 2 times 2 get cancelled. And if you think of it, I'm in a very similar situation. A situation which is very similar to that. I can now repeat this process. So for example, just like we made these conclusions from this equation, we can now draw conclusions from this equation. So the first conclusion will be that because b squared is twice of c squared, so b squared must be larger than c squared, because it is twice. The other conclusion is that whenever it is twice of something, b squared must be even. And if b squared is even, b must also be even. Otherwise, x square will not be even. Now, if b is even, I can, just like that, I can safely say that it must be twice of something. And let's call that something d, and then plug this there again, just like before. So now I am, that 2 and 2 that cancelled out. So I am now combining this equation, this assertion with this assertion. So I plug b is equal to 2d there. So b squared will be 2 squared is 4, and d squared, and this must equal twice of c squared. And if I again get rid of that 2 and 2 common here, I get c squared equals twice d squared, and actually it's the same case. So no matter what, and you can actually try this. I mean, no matter how many times do you repeat this process, this every time you get an equation of the same form, where the square of one thing is larger than the square of another thing. And each time the new number gets smaller and smaller. So you see, we started with a squared and b squared. It turned out that a squared was larger than b squared, but b squared was larger than c squared, the new number c, and that c squared, of course, now from this we can easily say that c squared must be larger than d squared, because it is twice. So you see, that new number c is less, so b squared is larger than that, and c squared is now larger than that new number. So it can go on, and each new number you find will be smaller and smaller and smaller. So if I now get rid of all this clutter, the conclusion I can draw from this assertion, if this is true, then it must be true that a squared is greater than b squared, and b squared must be greater than some other thing that will also be a square, and that must be greater than d squared, and so on. And this should not end. This is never ending sequence. This sequence of numbers is never ending. It will never stop, because you can always repeat that process. But now we have a serious problem. On one hand, we are saying that this sequence should never stop. But on the other hand, if you think about any sequence that is decreasing, you start from a number and then it gets smaller, smaller, smaller. Any sequence which is decreasing must come to an end, but because otherwise it is not decreasing. So we have a contradiction. If it were never ending, it should not have been decreasing. So, for example, if it were fluctuating, sometimes get up, down, get up, down, get up, down, or if it was increasing, if it were increasing, no problem. The numbers can get larger and larger and larger and larger and larger, and it would never end. Or if it was fluctuating, I can fluctuate, go up, down, up, down, up, down. But here, it's a different scenario. It is a decreasing sequence. The numbers get smaller and smaller and smaller. So ultimately, it should end up at 0, because all these are positive. There is no negative number. So it cannot cross 0. So that's the reason this assertion actually was wrong. Yeah, because if it were true, then we should not see this contradiction. So I hope that is convincing. So let me now tackle the other example, the other popular example of pi. Why pi is irrational? Now pi is actually, pi has two meanings. It's either the circumference of a circle divided by the diameter, that's one way. But I would like to introduce this irrationality by another argument, and that is much simpler. It's the area. Pi is the area of a circle which has a radius of 1. So if I have a circle with radius 1, the area of that circle is pi by definition. So let's see what can we do. Forgive me for my pathetic drawing. So this circle is inscribed inside a square, but there is also a smaller square which can be drawn inside the circle. So the area of this circle is between the area of this larger square and the area of this smaller square. This area must be less than the area of the larger square and must be greater than the area of the smaller square. The area of the larger square is what? 1 and 1, 2, and 2 times 2 is 4. So pi must be between 4. And if you look at this, if I complete this, you see that larger square is effectively broken into 4 smaller squares. And if you look at this line, this is the diagonal of that smaller square. So this area, below this diagonal, this one is basically half of that. So we have this 4, the larger square, the area of the larger square, divided by 4, because I have 4 squares, and then I am taking half of that, because this is half of that, and I have 4 of them, so I multiply this by 4. So 4, 4, and 2 times 2. So actually, pi is between 2 and 4. Now I can move on, I can make this finer and finer, and the next could be, I can actually improve this, and this pi will be between numbers that are much more refined, and this process can go on and on and on and on. I can make this approximation better and better and better and better. Now there are two possibilities. Either this will come to an end. So if it comes to an end, I will have a sequence of numbers, all rational, that comes to an end. Whenever it comes to an end, pi must be rational. The other possibility, that it never comes to an end. In that case, pi will be irrational. So if this approximation gets better and better and better and it stops, pi will be rational. And if it doesn't stop, it will be irrational. This was actually the main argument in my last lecture. Now, so the first possibility that sequence of approximations by ratios comes to an end, which would mean that pi is rational. There we have the flaw, because if it comes to an end, it means that we can accurately replace a circle with a polygon. Because if it stops, you are claiming that you have reached a polygon which has the same area as the circle. So you are actually trying to prove that I have found a polygon with enough number of sides where it becomes equal to a circle. Now that is wrong. Yeah? A circle is not a polygon. Yeah? Because if it were a polygon, it would not have been a circle. A circle is round and a polygon is not round. Polygon has edges. So this is a proof that it's a logical proof that pi is not rational, it is irrational. So I think that was enough for today. Next time we'll get more detail about the real line. There will be some more interesting discussion about the properties of real numbers. So stay tuned. Bye.